Have you ever really stopped to think about how we measure something as basic as movement? From a sprinter just exploding off the blocks to a planet circling the sun. It all boils down to two things, motion and time. So today, that's what we're going to break down, the science of how things get from A to B.
All right, let's start with something we all get. A race. Let's make it the 100-meter dash. The gun fires, the runners take off, and just a few seconds later, it's all over. Someone's won. In any race, this is it. This is the big question. Who's the fastest? Our eyes can tell us who crossed the line first, sure. But how do we know for sure? How do we prove it with cold, hard numbers?
Deep down, we all know the answer, right? If everyone runs the same distance, 100 meters, the winner is just the person who did it in the shortest amount of time. It's that simple. It's all about distance versus time.
But that's where things get interesting. How do we take that gut feeling of vast and turn it into a precise, actual measurement? Well, that's what science is for, and that's exactly what we're going to get into right now. So, before we can even start talking about speed, we have to agree on what motion even is. The textbook definition is pretty simple. An object is in motion if it changes its position over time. If it doesn't, well, it's at rest. Seems straightforward, or is it? I mean, think about it for a second. Are you moving right now? You might feel like you're sitting perfectly still, but you're on a chair on a planet that's spinning like a top, and that planet is flying through space around the sun. So yeah, you're definitely moving. It just goes to show you that motion is always relative to something else. And not all motion is the same, right? It comes in a few different flavors. You've got that straight line motion, kind of like soldiers in a parade. Then there's circular motion, like our Earth going around the sun. And you have periodic motion, stuff that just repeats over and over again, like a pendulum on a clock. And here's another really crucial idea. We have to separate steady, constant motion from, well, everything else. If something covers the same distance in the same amount of time over and over, we call that uniform motion. But think about real life. A car in traffic, a runner getting tired, that's non-uniform motion, where your speed is changing all the time. Okay, so now that we've laid the groundwork, let's get to the good stuff. Let's figure out how to get that one magic number that tells us exactly how fast something is going. Let's talk about speed. And here it is. This is the secret sauce. Speed is just the total distance you covered divided by the total time it took you to cover it. That's the formula that settles any argument about who is faster. And we can use this for anything. Let's say a train travels 240 kilometers in 4 hours. You just divide 240 by 4, boom, you get 60 kilometers per hour. Now, was the train always going exactly 60? Of course not. It stopped, it sped up. But this number, this average speed, gives us a really useful snapshot of the whole trip. But hold on a second. That formula, speed equals distance over time, it has two parts. Measuring distance is one thing, but measuring time accurately, that's a whole other story. It's actually been one of the biggest challenges in the history of science. I mean, our journey to measure time has been incredible. For ages, people used sundials and water clocks. Then a huge breakthrough came along with the pendulum. And now we've got these ridiculously precise quartz clocks in everything, all thanks to a tiny vibrating crystal. The whole story with the pendulum apparently started with Galileo. The legend goes he was bored in church one day watching a lamp swing back and forth. He used his own pulse to time it, and he realized something amazing. Every single swing took the exact same amount of time. And that one little observation, it changed everything. It gave us a brand new, super reliable way to keep time. We call the time for one full swing an oscillation, or its time period. That simple repeating motion was the heart of clocks for hundreds of years. Okay, so we've got distance, and thanks to guys like Galileo, we have a way to measure time precisely. Now, when you put those two things together, you don't just get a number for speed, you get a story. And the best way to see that story is to draw a picture of it with a graph. And making one is actually pretty simple. You draw your two axes, time goes along the bottom, distance goes up the side, you pick a scale that makes sense, you mark your data points on the graph, and then you just connect the dots. That line you just drew, that's the story of the journey. Because that's the thing. It's not just a line. It's a whole narrative. Graphs take all of those boring numbers and turn them into a visual story of motion. The shape of that line tells you everything without you ever having to look back at the data. And the most important thing to know is this. If that line on the graph is straight, it means the object is moving at a constant speed. That's what uniform motion looks like. And the steeper the line, the faster it's going. It's that easy.
This is where the graph becomes a superpower. You can find information for any point along the journey. Like for this bus, what if you wanted to know how far it got by 8:15? You just find 8:15 on the bottom, go up to the line, and then look across to the distance. The graph gives you the whole story, not just the points you measured.
So, let's wrap this up with one last thought. We know a straight line means a constant speed. So which one of these would show a car that's actually speeding up, accelerating? Think about it, because this isn't just a pop quiz. This is about learning the visual language of physics. Once you can read these stories, the flat lines of being stopped, the straight slopes of cruising, and the curves of acceleration, you can understand the motion of anything, just at a glance. So what other stories do you think are hiding in the simple lines all around us?